All right, we're getting through this chapter. We're down to 2.6, implicit differentiation. Excuse me. All right, so first thing we'll start with, noting the difference between an explicit and an implicit equation. So everything that we've studied so far has been a function of the form y equals f of x. So we've been able to basically solve for y, you could say, get y on one side of the equation and get some function of x on the other side. Any equation like this where you can solve for one of the variables in terms of the other is called an explicit equation. So sometimes we are faced with a challenge in that we cannot get one of the variables, let's say y, completely isolated on one side of the equation in terms of x. Here are some examples of equations that are explicit, and then the others where we can't solve for one of the variables, which we call implicit equations. So y equals 3x minus 1. This is a line, right? So it's obvious here we've solved for y. So you could say that this is an explicit equation. We got y by itself. Y is determined explicitly by x. Here again, y is some function of x. Now, even though this is complicated, still we can determine y if somebody gives us an x. Here, I kind of switched it up on you. This is still an explicit equation because you can get x in terms of y. So again, one of the variables can be written completely in terms of the other variable. So these three equations, I challenge you to try and solve for y or x in either of these three equations. Now, it can be done, like for example, this first one here, you could move your x squared over, so subtract x squared, and then you could take the square root. The problem is when you take the square root, anytime you take the square root in an equation, you have to take two scenarios, the positive and the negative, so the plus or minus. So even though you'll get y written in terms of x, you'll have two different scenarios to consider. So really y is in terms of two different functions instead of just one. So again, this is an implicit equation. And then these, I'll let you play with these, and I'll mess with these in class too. Try and get y by itself, isolated, with no y on the other side of the equation, and you'll see you're going to run into some problems. So that's just to get us to understand the difference between explicit and implicit equations. So here is a graph that x squared plus y squared equals 16. That was our first example of an implicit right here. Right here, right? X squared plus y squared is 16. So we can see that if you graph this, it's a circle, right? We should all recognize x squared plus y squared equals 16 as a circle. The thing is, this fails to be a function. Remember the vertical line test. If we try and plug in some value of x, let's say 2, then the y's that come out are actually up here and down here. So we have two possible y values for the x value 2. That's why it fails to be a function. One input should be one output, not two outputs. But we still have the idea of tangent line to this. So let me show you, if I move this around, if I were to plug in that 2, right, then my y value, one of my y values should be right here, and the tangent line should be here. So I should have some concept of a derivative here still. But the problem is there's another one down here. So how am I going to determine which of these it is, and how do I get this answer versus this answer? And then as I move around the circle, you can see that I've got basically two tangent lines for each x value. So we will investigate in class how we're going to figure this out. It's going to require what's called implicit differentiation. So let me close this note out and get to the next one. Here's another equation. It's an implicit equation. Very difficult to solve this thing for x or y. Actually, I'm going to do that in class just to show you how to do it. It's kind of fun. But this curve right here looks like this. And you can see, again, it fails the vertical line test right here, and it fails it right here. But I should have some points. So, like, let's see. For the x value, it looks like 4. I have this tangent line right here. But I also have one up here, right? I should. Boom. Yeah. So, again, how am I going to determine which of these answers it is? And as I move around the curve, for every x value, I should have some tangent line. But when I get in the middle here, so right now my x value is in here, and the computer's like, wait, I don't know what to do. That's because there's no graph here, and so that there's going to be no tangent lines. But as soon as I move over a little bit further, you can see I start to get tangent lines again. So question is, how do we get these again, right? So we'll be doing that in class. And let's see. All right, this is just a quick little summary. As we can see above, the curves are not true functions of x since they fail the vertical line test. So given a single value of x, there are multiple outputs. This means that given a value of x, there are multiple tangent lines. To obtain each of them, you will need to know more than just the x value. I should spell that right. And you should need to know more than just the x value of the point. We will also need to know the y value. So we're going to be studying what's called implicit differentiation. I'm going to do a bunch of examples in class just to get us used to it. It's really kind of different than anything we've done so far, but the power of implicit differentiation can't be overstated.